Hi guys, so now we're going to get into more of the honors topics within the equilibrium unit. So a lot of this is going to be calculations. So why do we care about equilibrium? So basically, when you have a forward and reverse reaction going at the same rate, what did we say happens to the concentrations of the reactants and the products? They stay constant. So when we're in equilibrium, we know what the concentration of the reactants and the products are over an unlimited amount of time because they're never going to change. So let's write that down. We know the concentrations. Do you guys remember what the unit is for concentration? Do you think that's solutions? So we're going to be seeing molarity, capital M, of reactants and products after an unlimited amount of time. So a mass action expression tells us the ratio between products and reactants at a certain temperature, and it's abbreviated as the equilibrium constant, KEQ. And when you're writing this, you're basically dividing. You're doing, brackets mean concentration. So whenever you see brackets, we're doing the products or the concentration of the products. That's what the brackets mean, over the concentration of the reactants. And you only include aqueous and gases in your equilibrium constant. So if you see a solid or liquid equation, you could ignore it. And you also have to pay attention to the moles of each substance in the reaction, okay? So as an example, we'll do this one together. If I want to know the KEQ for this reaction, I would do the products on top. So my products are, I just had NH3, that's my product. Brackets means I would be putting its concentration in this spot. And see how I have 2 moles of NH3? Whatever the coefficient is, that's going to become your exponent. So it's going to be squared. On the bottom goes the reactants. So my first reactant is N2. I only have 1 mole of N2, so it doesn't need an exponent. And I'm going to multiply that by my next reactant, which is H2. And because I have 3 moles of H2, this is going to get cubed. And that's going to be my equilibrium constant. Now this is a formula that you're setting up to eventually go plug numbers into, but for right now, if you want to pause the video, if you go to page 2 of the worksheet packet and give that a try, it's just practice setting these up. Okay. Some things you should know when you're given a KEQ, like if you're given the actual numerical value for it, that can tell you something about the reaction also without knowing anything else. So if my KEQ is greater than 1, that means when I'm dividing, that means that this number, the top number, is bigger than the bottom number. That's how I come up with a bigger number when I divide. So if my top number is bigger and my top number is the products, if your KEQ is greater than 1, that literally just means that the amount of products, the concentration, is greater than the amount of reactants. So the forward reaction is favored. So it's a little bit easier for that reaction to go in the forward direction. If your KEQ is less than 1, that means you must be dividing a small number by a big number to get like a decimal. So that means that your bottom number is the big one here. So I'm going to have less products and more reactants. So if it's easier to make reactants, that means my reverse reaction is going to be favored. That's if you get a decimal for your KEQ. And then finally, KEQ equaling 1. How do you get 1 when you divide 2 numbers? Those 2 numbers have to be the same numbers. So the concentrations of the reactants and the products are going to be equal to each other. Now, in equilibrium, I've been drilling to you guys, okay, if you see the word concentration, never use the word equal to describe it, use the word constant. concentrations are always constant. They don't have to be equal. In these very, very, very few cases that are very rare, they can be equal to each other, but it's not a necessity for equilibrium. Okay, so the reaction quotient, the QEQ, it's the same thing as the KEQ. You're taking your products and you're dividing them by your reactants. But when they call it the QEQ, that means that the reaction might not be in equilibrium. So those concentrations that you're plugging in might not match what you would get if you solve for KEQ. So this will make more sense if we just do one together. So let's look at this reaction, the KEQ, right? I need to do my products. So my products are AB2 over, my reactants are A and B. And I have 2 moles of B, so that means I'm going to square that. Okay? So now here's what I was talking about before. They actually gave us concentrations here. So if I plug those concentrations in, I can actually solve for a number for KEQ. So AB squared is 0.5, A is 3, B is 2, and that's going to be squared. And if I solve for KEQ, I get 0.042. So that's my equilibrium constant. And like we said before, guys, if I think about where that number is, what kind of number it is, it's less than 1. So that means that for this reaction, the reverse reaction is favored. It's actually easier to go into reverse than to go forward. Okay. So now I have a new experiment, and I want to know if it is at equilibrium. So if I'm not sure if this is in equilibrium or not, I'm going to call this the QEQ instead of the KEQ. But like I said before, guys, it's literally the same exact thing. We're going to plug in the numbers they give us. So I have 1.25 for AB. I have a molarity of 2 for A. I have a molarity of 4 for B. Okay. Now, if you throw that in your calculators and solve, you get 0.039 as your QEQ. So I want to know, is it at equilibrium? If it was at equilibrium, the ratio of reactants to products would have to be the same as in the KEQ. So is 0.042 equal to 0.039? No. So then this reaction is not in equilibrium. And your explanation is literally because the KEQ and the QEQ are not equal to each other. Okay, so at this point, guys, I want you to stop here and do page 4 of the worksheet packet, and we're going to get into a little bit more complicated KEQ problems in the next video.